Thank you, everybody, for attending my talk. We're going to be talking about writing a Zephyr application in Rust, and this is just going to be an overview. There's actually a lot that is involved when talking about Rust and Zephyr, just because there's a fair bit of intersection between just Rust, kind of in embedded, versus kind of the implementations that Zephyr has. So this is really just going to be a high-level overview of, how do we get started in Rust? What are some of the problems personally that I've encountered in Zephyr that Rust can address? And then just a real quick kind of hello world demo that I wanted to show. And then what are some next steps that are interesting for me to kind of investigate further? So like I said today, with usually all of my talks, I start with the motivation, why it's relevant to why my talk is relevant. Then we're going to dive into getting started with Rust in Zephyr. So again, just a really kind of high level overview of, what are the steps involved. It's well documented, but the documentation isn't entirely correct. So I just wanted to note out some caveats there. And like I said, just demonstrate a real hello world demo, writing a Rust application, just running the sample that's provided in Zephyr, and then just briefly go over the code that's provided to us, and then understand how the implementation there is relevant to Rust as well, and then some summary and next steps. So just a little bit about myself. I'm an embedded software consultant in New York City, out in the United States. That's my email address. That's my LinkedIn and GitHub. You can check those out to see kind of the things that I'm working on. Mainly, I do design work, medical devices, LiDAR, commercial kind of products, and also have worked on one custom ASIC that's leveraged Zephyr as part of one of the cores in the chip itself. My main expertise is in Zephyr, but also in embedded Linux and Yocto. I also hold training sessions. This is one training session that I held a couple of months ago that was specific to embedded Linux and Yocto. We're gonna be holding more training sessions in New York City, or really close to New York City, in a few months that's specific to Zephyr. So if you're interested, I encourage you to sign up for the newsletter that I kind of distribute every month on more information. So motivation, right? So I've worked on a fair number of Zephyr-based applications, right? Both adding drivers, writing applications, both simple and fairly complex. And so I've had numerous issues that are kind of related to memory, and they can be summarized in, these are the two most difficult memory-related issues that I've encountered. One is data race, and the other is Stack Overflow. So what is data race? It's essentially when you have kind of multiple threads that are both accessing the same kind of resource. Typically it's a variable, and you don't have any sort of synchronization, right? So generally that's what a data race is, right? You don't have any kind of form of synchronization that's provided for, let's say, multiple entities that are accessing one particular resource, most likely a variable. In my case, it's been variables like the underlying kind of implementation is really nice. It becomes more obvious when you're using like an actual like hardware peripheral or resource. Obviously like you have to have some sort of synchronization mechanism, but when it comes to more nuanced implementations where you have a variable, that can kind of sneak through the cracks because it's not an obvious requirement that you have, right? So the other issue is that you can have also incorrect synchronization, right? So again, this is just some personal experience, right? I've seen issues, or I've implemented incorrectly, K no wait versus K forever if you're kind of accustomed to Zephyr. So choosing the right one to use depending on what your thread is doing specifically, it can be really important, right? So if you choose the wrong one in the wrong thread, that can affect your entire application because you may be confused as to, well, which is the thread that's writing to a particular variable and which is the reader, or they can be doing both. And now you need to sort of manage like, okay, when do you want one to immediately kind of return or the other to kind of just block there waiting for that resource to become available. So managing that sort of relationship can be tricky. And if you pick the wrong one, and again, if in a lot of these instances, we'll see that the issues may not be obvious. They may be really subtle, and they may happen in certain instances. So it can be all working fine, and now your device is out in the field. You run into this really weird scenario, and now your customer is complaining that it hasn't crashed, it hasn't rebooted, but it's sitting there doing nothing because one of your threads probably is blocking and it shouldn't have, right? You haven't implemented the solution correctly, right? And the problem that just scales worse, it gets worse as you add more threads, right? So as multiple things need to interact with, let's say, the same set of variables, right? As you increase that problem set, the possibility that your problem increases as well. So, data race can be a really kind of nasty problem when you're writing specifically kind of Zephyr implementations. Stack Overflow, and in my kind of experience, I've noticed this misconception, right? Say, like, people generally say, well, how can I experience a Stack Overflow? West, like when you build a Zephyr application using West, it shows you at the end that, oh, this is what my flash and RAM utilization is, and it actually complains as if either is overused. So why are we worried about Stack Overflows when we're writing a Zephyr application? If I'm going to blow out my RAM usage, well, it's going to show me, right? And here's kind of an example where I kind of artificially blew up my RAM utilization for the simple kind of hello world. And it does complain, but the question is, well, that a common misconception that I encounter is, why do we need to worry about Stack Overflow when Zephyr is going to tell me, or Wes is going to tell me, that my RAM utilization is going to blow up? And the misconception is that your RAM utilization doesn't necessarily have anything to do with how much stack you're using specifically, right? Because almost everything in Zephyr is essentially kind of configured with a stack size. So your main thread, right, there's some defaults that are baked into it, but again, there's configuration options that are that you specify that dictate how much stack is being used for each of these different kind of elements, right? So your main thread, if you're, again, accustomed to Zephyr, right, that as one of the mechanisms when you create a new thread is to specify the stack size, right? The main work queue, the system work queue, also has a particular stack size. If you spin up another work queue, that also has a stack size, right? ISRs also have a stack size. So just because West is telling you, if you've overblown your RAM by a fair amount, that's like just a fundamental problem, right? That you have to resolve that first. But identifying whether you've blown through the stack, it's difficult to identify during compile time. So typically for me, right, when I've had complex applications, what I would usually encounter is, hey, or as soon as I start debugging the application, right, running the application on the custom board in my lab, all of a sudden, right, it's just going to stop, right? And then when I attach a debugger to it, I see that, hey, Zephyr's entered kind of a halt fart handler, right? You typically just see just sitting in the fatal.c file, and it's sitting there in an infinite loop, right? And then my typical, again, either I can use stack canaries to identify okay, where this problem is it a stack problem? And then incrementally, I slowly start increasing the stack size for my thread that's kind of, being where the issue is. Or I go back to the thread implementation and say okay, why is this consuming so much stack space? Can I make this implementation a little bit better? So again, right, the problem with this sort of issue is that you can't figure out that you're running into a problem until runtime, right? There's no real way to identify the problem ahead of time. Are there, what about some other kind of memory-related issues in Zephyr? I generally try to avoid kind of dynamically allocating memory. I try to make sure that whatever application that I'm targeting, that I have just statically allocated memory that I don't necessarily have to dynamically allocate. But if you need to, then you can use kmalloc in Zephyr to be able to do that, and that's specified by this kconfig heap mem pool size. But again, right, there's a lot of responsibility that you have when you start dynamically allocating memory, right? So you're responsible for freeing the memory after it's being used, right? And you make sure you have to do it correctly. If you forget to do it, right, then that leaves less memory for you to use later on. If let's say you need to allocate more memory, and you have to make sure that, hey, if let's say as your application gets more complex, let's say you've allocated some memory in one thread, now you're passing that variable over to another thread, and now in the original thread, you freed it up inadvertently, right, incorrectly, and now in the second thread, now you're starting to use it, right? So that's a common kind of use after free issue that we hear about. So again, there's a lot of onus on you when you start dynamically allocating memory to make sure you're actually using it correctly, freeing it correctly to make sure there's no leaks. So how does kind of Rust help with all of this, right? So we talked about 3 issues, right? So for me personally, right, Rust helps address the issues kind of that are outlined above, right? And the crux of it, what's central to all of this is a memory kind of ownership model that Rust at compilation level kind of gives to us. It tracks memory ownership, right? So what that means is it can identify memory that's no longer used, and it automatically frees it first. So there's less responsibility on the developer. It's on us as developers. And there's certain set of rules that we have to follow when we're writing a Rust application, right? Regardless of whether it's embedded or not. These ownership rules are baked into the compilation process. And if we violate these rules, then the compiler actually throws us an error. So that, for the most part, right, that addresses that compilation error, helps eliminate a lot of the runtime errors that, these 3 issues sort of highlight. So some kind of examples of this is that if let's say you try to access memory after ownership has been transferred, right, you're going to get a compilation error, right? So you can transfer ownership of a particular variable from one owner to another. And if, let's say, you try to use that variable again after ownership has been transferred, then the compiler is going to notice that and it's going to throw an error that you can't do that. Also, if you're kind of modifying data across threads in an unsafe manner, there's a compilation error. And what does unsafe mean? It basically kind of goes back to this memory ownership model, right? So unsafe is if you're accustomed to Rust, it's a common kind of paradigm. And there's a certain set of rules that you have to follow to ensure your implementation is safe. And if it's not safe, or if the compiler has determined that it is not safe, it's going to throw an error during runtime. And the advantage to this is that it forces us to think about problems sooner rather than later. So again, if let's say, if you're not writing Rust, right, a lot of these errors and issues can be nuanced and subtle, and you don't find out about them until runtime, right? And God forbid you run into your customer starts complaining, and there's this really nasty bug that you're encountering. Debugging that sort of issue can just become a nightmare, right? You have to reproduce it, right? You have to figure out what sorts of conditions cause that error to occur, and now you have to be able to reproduce it if you can't even get, let's say, the device back, right? And now you have to go down the rabbit hole of actually fixing the issue itself. But if, let's say, you have some sort of framework, right, that Rust kind of provides, right, that you can identify these sorts of issues or these sorts of errors that contribute to these issues ahead of time during compilation, well, you have a leg up, right? You have a head start on addressing some of these issues, because now during compile time you can at least address the issues that you've encountered, right, or that you may encounter in the field. So again, right, a lot in some of the projects that I've worked on, right, a really bad feeling is when you start thinking about the problem that a customer is encountering, or even you, as you're debugging and testing your implementation, you're encountering after, let's say, spending weeks, months on the implementation, and you're like, oh crap, I gotta rethink how I architected this application because this just doesn't make sense, right? That's the worst for me. That's the worst feeling that I can have, because now I've wasted kind of all these weeks and the weeks and months. And what ends up happening is, like, I have to shoehorn or hack together a solution that at least, gets something out the door, right? So with Rust, the advantage is that, again, because it handles a lot of these memory management issues for us, or tells us about these issues during compile time, you can know ahead of time, instead of like spending weeks and months implementing and testing your application, most likely, you'll find out within a few days that, oh, there's a major issue in terms of how you're managing memory in your application. And then you're forced to essentially kind of restructure and reorganize your application and redesign it, right? So again, it all comes back to knowing about the problem ahead of time instead of, waiting for the last minute to be told essentially that, there's a problem in your implementation or in your design and you have to do something about it. So then, if you're new to kind of this whole sort of thing, is like, well, the question is, we're talking about Zephyr, we're talking about Rust. Is there like essentially like another version of Zephyr that's written entirely in Rust? No. So, one of the cool things about Rust is that both it and C can coexist. Rust leverages what's called a foreign function interface, which is the paradigm to go between Rust and C. And the challenge doesn't become, well, how do we write Zephyr in Rust, right? That's not the challenge, right? Because you don't need to kind of reinvent the wheel. If you follow kind of the Linux kernel, they sort of kind of experience the same sort of kind of challenge. It's, well, how do you figure out where the right boundary is, right? What the dividing line is between the Rust side and the C side in Zephyr, right? How do you figure out where to draw that line? And this is the job of the community and the maintainers. And that's not an easy problem to solve, right? You have to think about not just only the technical details, but in general, how are people going to be using now Rust with Zephyr, right, to make sensible decisions. Just beware that, those are three problems that I've kind of identified: data race, Stack Overflow, and just, if you're dynamically allocating memory, Rust can help address some of these issues, but it's not some sort of like magic bullet, that you can say, throw Rust at it and it's going to solve like some other kind of weird issue, right? Your job isn't done, right? Just because you can leverage Rust doesn't mean you can like stop thinking about things, right? It's not going to address performance issues. It's from my kind of perspective, it's mainly to help me, again, it's a tool, right, for me to use to help me, to tell me when problems are going to occur in my implementation. But again, it's my responsibility and my job to make sure that, hey, I'm implementing things correctly, that I'm still tracking my performance metrics to make sure that the implementation is correct. And again, whenever we have this new tool, there's a tendency to like, just everything is now a nail and I'm just going to use Rust and everything. No, just be aware that, there's an effort going on to incorporate Rust into Zephyr. And from my perspective, I think this is what, these are the three issues that it solves. But again, we still have to do our jobs, right? We still have to make sure that, we understand what the advantages and also disadvantages are, right? So, because again, we're working, right? We have limited amount of time. So we have to understand the trade-off between, how do we incorporate Rust versus just keeping things, in C as it is. So how do we get started with Zephyr, with Rust in Zephyr, right? So obviously, right, you have to install Rust. So this is straight from the Rust kind of homepage. We need to install Clang also. Again, because Rust uses, and Zephyr in Rust uses the FFI to basically provide that interface between Rust and C, right? We also need to install Clang because there are parts of the Clang toolchains that are really good at kind of supporting that interface. And of course, right, if you're not new to Zephyr, you have to set up the Pi, the virtual environment, set up the appropriate tools, and then we can get started with actually the Rust side of things, right? So we can install the latest release of Zephyr using West init. And then the important thing is in the middle here. We can basically, let's see if I can do this. Oh, that works. Right, so what we need to do is we need to tell West that we want to add support for the Rust kind of language modules in our repository, and then we can just run West update. And then finally, right, there's some great sample code in here, right? CD in modules lang Rust. We go into here. This is basically the demo that I'm going to be demonstrating today on this target, and then we can just do hello world, and it all works. No, it doesn't work, right? So the repository that's tied to version 4.2.0 doesn't have to, it has some bugs, right, in the Rust implementation. So instead what you need to do is you just need to check out the main branch, right, pull in kind of the latest main, and it builds now, right? So again, right, still a work in progress, right? This is not ready for prime time, but it's, just something to kind of explore and to stay up to date on. But once you do that, then you have, your final binary that you could load onto it. So let's just kind of see like a quick demo of Hello World in Rust on Zephyr. So this is a board that I really like to use. It has a whole slew of things, and it's only for $50. I think on DigiKey this morning I saw it for about 45 euros. So I think it's pretty cheap for what it can do. So low power MCU, it has BLE, Wi-Fi. It also has sub gig RF, which is pretty neat. NFC, and it has a whole, like I said, bunch of sensors. I like to use this board for a lot of the Zephyr things that I do. So here is the demo. It's nothing, how do I, oh, here we go. Nothing kind of, too exciting. Kind of got past the exciting part when it failed to build. We can build, going to terminal into my board on the bottom here. Okay, and then I'm just going to flash it. And great, and we see on the bottom, we have the basic kind of hello world application running. So again, just very kind of minimal gymnastics that we have to do, but at least at a minimum we can get hello world, right? But this is not the end of it. Let's just kind of dig a little deep into kind of the start with the sample that we started and understand like how Zephyr basically ties Rust and C together to give us kind of this or to facilitate this sort of implementation, right? So one of the things obviously we need to do is like we need to enable Rust kconfig, right, in our kind of application, and we'll get into this kind of main stack size like later in the next couple of slides, like why this is important. But the other thing that's important to note here is that this kconfig for Rust allocation is, again, there was work done to enable Rust support in non-Zephyr kind of bare metal applications. So there's a lot of implementations that's already done for, just non-embedded kind of Rust, but also an embedded Rust too, right? So there's already kind of implementation that's already there, and it's important to kind of for Zephyr, right, to kind of manage, because Zephyr also has its own implementations. So it's a challenge. It's an interesting challenge to figure out, well, where's that dividing line between what Zephyr's custom implementations are for Zephyr, for Rust, and then where we can just bring in kind of Rust implementation natively, right? So this config Rust alloc is one of those where it enables a crate, which is just kind of like external libraries, right? If you're not familiar with Rust, to basically dynamically allocate memory from the heap, right? Again, this is not necessary for this sample, right? But it's just kind of something to point out. And kind of going along kind of with that statement, right? So there's three main kind of crates that are generally used or in general kind of leveraged by Zephyr. So core, right? So that's basically the crux of the language itself that's specific, that's provided by the language natively, and then that's supported by all architectures. There's the alloc crate, which provides a subset of the standard library for just memory allocation, right? And so if you want to leverage this crate, what you have to do is you have to provide an implementation that does the allocation for you, right? And so that's what this whole kind of config Rust alloc is. If we're doing kind of more interesting memory allocations that are more dynamic, then we would definitely want to use config Rust alloc in that sort of application. But in this case, right, I mean, I think it was just included in here just for demonstrative purposes, but it's nothing to, we don't really need it for this Hello World application, right? And then there's the third thing which is the standard library. And again, like that has a lot of features in it, like file system networking. And typically in embedded applications and also in Zephyr, we don't usually include it, right? So typically, like you'll see a lot of in Rust applications that are targeting Zephyr or really any embedded kind of application, you'll see like the attribute that's defined to do like no STD, right? Which means not to use a standard library. And then if we look at the cmake list.txt file, right, we can see there's this cmake function called Rust cargo application. And what this does is, again, if we go back to basically like the foreign function interface, right? We have C, we have Rust that are talking to one another. You still need, right? It's still going to be, Zephyr is still going to be launched from the C side, but you need to have some way of instructing Rust to launch into your kind of informing C to basically jump into your Rust application on the Rust side, right? So that's what this kind of cmake function does. It makes this kind of Rust function available from the C side. And then we have the actual kind of source code, right? So source lib.rs is in the sample, in the hello world sample. But if you're familiar with Rust, you'll notice that it's usually the entry point for any Rust library crate. And the other thing that we have down here is that we have this thing called Zephyr. Basically, so first things first, right? We have this Rust main here, which is called by the C side, right? And again, this is made possible by the CMake function Rust cargo application. And then in here, right, we need to make this unsafe call to this set logger that Zephyr provides, right? And then this returns an option, right? And this is essentially like, again, we go back to this thing, this is a common theme where Rust offers some feature, but Zephyr kind of also provides this optimized kind of feature implementation for, let's say, a particular architecture. How do we kind of, make the two kind of play nicely with each other? So, there's some glue logic and this is kind of a recurring theme as you dive more into the Rust side of things in Zephyr, is that there's typically kind of glue logic to manage both the Rust and Zephyr side. So in this case, this is like for logging, right? So basically, essentially, there's a portion of the Rust logging system that you leverage, and then you basically kind of short circuit that into the Zephyr side, and that's kind of the glue logic that we're seeing here essentially. And then again, if you're familiar with Rust, there's this TOML file for cargo. The top portion is the typical things that are kind of associated with Rust, and then this middle part, right? Again, we want to even if you're not familiar with Rust, but you're coming from a Zephyr background, right? You know or should know that typically, like your application code is not the final application. It's compiled into a static library, and then finally all of the static libraries that are the static library that's compiled for Zephyr proper, right? And then your application, they're linked together to form an ELF file, right? Same thing happens here, right? Essentially, we're instructing Rust that we're going to be creating the static library, right? And then the last part here is that we're defining, we're specifying additional dependencies, not only for Zephyr but also for this logging crate that we use here effectively. So that's kind of it. That's my talk in a nutshell. So just to rehash what we did, we understood the value that Rust brings to embedded software applications. So again, right, just to keep in mind that, just like any other new framework, it's just a tool, right? It's not going to solve all our problems, but it does help to mitigate some kind of nasty problems that we may encounter. So if your manager comes to you and says, hey, can we're seeing these problems out in the field, right? Can we just do Rust, right? Let's just do Rust and like fix everything. It's like, no, that's not the case, right? Like you have to kind of still think about what the implications are, not just from a technical point of view, but also, right, we have limited time, like how much, is the juice worth the squeeze, right? Like as we say, is the amount of time that you're going to put into rewriting applications in Rust, is it worth the time that you're going to be saving, right? So that's a decision that you have to make, you have to make with your manager. And then, we understood how Zephyr kind of intelligently leverages Rust as a force multiplier. So like I said, Rust has a lot of features in it that have been implemented for embedded kind of applications in addition to kind of non-embedded applications. And it's an interesting challenge because Zephyr there's a lot of overlap between what Zephyr offers and what Rust offers. And so it can be used pretty nicely because there's a lot of features that Zephyr can leverage from Rust that can enable it to be a force multiplier, right? So you have this existing code base that you can essentially reuse in your RTOS to be able to allow you to kind of manage some of the memory issues as well. And then we, like I said, dug briefly into the code base, not too extensive, right? Because I only have about 10 minutes in my talk, and then we learned kind of how to get started. So what are some next steps, right? So review more complex applications. The actual samples in the Rust repository for Zephyr, there's some pretty neat samples, right? It gets into a lot more. You have a few kind of multi-threaded applications that take advantage of synchronization. And again, we see the same recurring theme, right? Of using existing Rust paradigms in Zephyr, right? So if you have like multiple tasks that are doing things, right, there's example code of how we can leverage what's called the embassy executor crate, right? Or, if you have thread synchronization, right, how do you leverage the embassy sync crate, right? So again, it's an interesting, if you just look at like the 4 or 5, even the Blinky sample that's in Rust is a really good starting point to understand, how do we expose like device view configurations, right, to applications. So if you're, again, accustomed to Zephyr and, at the top, usually you have your node label, right, and you have your macros that are specifying like, okay, that you can leverage in your C code. Well, how would you do something like that in Rust? So the Blinky application is a great way to kind of just see how to do that. And then, sometimes you may want to compile different portions of your code depending on which K-configs are enabled, right, even in your application. So it's a common thing to do in C, but then how do you do that on the Rust side? So again, the sample code has pretty good examples on how to do that. So I encourage kind of everybody to, look at the samples that are provided, and then and it's a great way. The way I kind of got into this is the Rust programming language book is a really good starting point, and then you can start seeing like some of the paradigms that it specifies, or some of the constructs of the language in the Zephyr sample, and then you can start relating the two back and forth. So start with that, and then start looking at the Zephyr kind of Rust samples. And then, you could just grep through it. Honestly, it's not that much code to just grep through the Rust kind of implementation in Zephyr, and then understand, like, work your way backwards. So the next step that's kind of really interesting to me is this whole concept of, so again, if you're familiar with Rust, you know that there's concept of like library and binary crates. One of the most fascinating things, and one of the biggest reasons I really enjoy using Zephyr, is the testing paradigm. So again, like a personal best practice that I usually leverage in all my Zephyr applications is that my application source is very minimal, right? Under app source, I just have main.c, and it's like maybe like 10 lines of code. And all it's doing, it's just initializing basically a few application libraries, right? All of the actual implementation is under a lib folder that, I use some CMake gymnastics to, so it's well defined, right? So that you can make it as part of your final implementation. And what that helps me do is now I can easily write unit tests, right? So my application source code that's actually going to run on target hardware is minimal, because all the thread management, all the actual real implementation is in the library code. And then what I can do is when I'm ready to write unit tests, right? All I need to do is, it's just a different application. I can reuse the same functions, right, that I use for my library side, and I can write really sophisticated, really kind of well thought out unit tests just because of this paradigm. And this fits really nicely into how Rust does things, right? Rust you have a library crate, like your source code, you have a library side, and then you have a binary side. So I want to explore, how can we kind of enable that sort of paradigm as well too? Like, does it make it more easier for developers to kind of see that? Because most of the time when I see like a lot of, other engineers kind of writing Zephyr based applications, like, they don't kind of see the value of that, right? Like making your application source code really minimal. But I think when you start thinking about Rust now, like it's just built into the language itself. So I'm hoping a lot more kind of embedded engineers can kind of think through that, because it's really important to write unit tests. And finally, the last thing is, like drivers. I have a few PRs that are open for kind of new device drivers that, I need to kind of wrap up. But, it'd be interesting to see like, hey, like if I were to take a stab at writing a device driver in Rust, kind of what does that look like, right? I mean, maybe, we can take some inspiration from the Linux side, right? The kernel side, to understand like, is that a strategy that we can leverage in Zephyr to write device drivers, or what does that look like, right? So, I have a few PRs. I have another kind of driver that I need to write for, another device that I need to write a driver for. So maybe, I'll just close these out in C and then write the new one in Rust and see kind of where that takes me. Because again, there's a lot of infrastructure that needs to go in place before you can start writing, and a lot of thought that needs to go in before you can just, write a device driver in Rust, right? There's a lot of APIs. Again, you need to kind of think about where that dividing line is between Rust and C, what makes sense. So that's it. I think I have 6 minutes for any questions. Yeah.
How do you assign the memory to the stack of the Rust part of the firmware? Is it not also limited? So if so, how does it help you with stack overflows?
So I think it's more I think it's more related to like ensuring that. That's a good question. Yeah, I have to look into that. Not entirely sure. Anybody else? Yeah.
So we talked about the phrase about memory alloc,
Mm-hmm.
and that can be turned on and off. Does it impact binary size of the final application? Or what's the point of disabling allocation, dynamic allocation?
What's the point of disabling it? Or yeah, I mean,
because I feel like you lose a lot. If you
a functionality.
variables in Rust code, I feel like it's a bit it's not really rusty.
Right. Yeah, I mean, yeah, that's a good question. Like, I need to kind of see what I didn't see any kind of noticeable differences in the binaries when I saw it, when I kind of disabled it. So I think like, yeah, I mean, I think in the case of like the sample that I showed, right, like you're not really doing much, but yeah, I think in general you just want to keep it enabled. Anybody else? Yeah.
How does prevent backending?
Because of the ownership model. So like if let's say you transfer ownership between like one thread and another thread, right? And now, so like only now, that let's say variable is only writable by the owner, right? That's has it, right? So now there's only one single owner at any given time, whereas without Rust, right, you basically have free reign because there is no kind of inherent ownership model. So if let's say two things are, it's like the typical kind of read, modify, write problem where two threads are, let's say, writing to the same piece of memory at the same time, unless you have like synchronization in place, right? Depending on who gets to that memory first, that value may not be deterministic. So with Rust, it's like, well, there's a distinct owner, right, at any given time for a piece of memory, so only they can write to it. Right. I mean, so with C, like you have to remember to do that, right? Whereas Rust, it's just given to you by the language itself. Like you don't need any other kind of synchronization kind of constructs. Yeah.
But don't you still need some sort of synchronization, and is it already supported in Zephyr? Because I mean, with ownership, only one thread could have ownership to one variable, and you can't pass it to another thread. But you need ARC and you need all those sort of stuff. I mean, for this you need async Rust, and is it supported already in Zephyr?
I think it leverages kind of like when you have like these different kind of taskings. Like I think like again you take advantage of like it's that dividing line, like because Rust already has like some of the kind of synchronization metrics. Like again, yes, for resources, yes, you need and Rust kind of has these synchronization mechanisms that are built into it. But you're taking advantage of what's already in Rust, and then it's kind of the implementation underneath that may be like architecture specific, right? That you may want to take advantage. That it's interesting, like how kind of Zephyr uses like the existing Rust crates, right? And then where it kind of provides its own implementation. Does that answer your question? I don't know.
But other you have sync, embassy sync stuff on your almost last slide.
Yep.
There. So those are already supported, or that's something that's going to be supported?
No, these are already. So this is what I want to explore. Like Zephyr already has this. This is, I guess, next step saying that if you go to the samples, like they have like an embassy sample that you can look at to see like how do multiple threads kind of interact with each other using the embassy. But I guess my point is that it's not strictly just Rust, right? It's not like strictly like, oh, here's just leveraging kind of embassy, the embassy executor crate in Rust. there's also a Zephyr side of this that like, oh, if you look at the actual kind of OS implementation of it, right, it's also has its own sort of implementation that builds on top of what Rust already has. Okay? Yeah.
Is there any computational cost in using Rust compared to C?
No.
Not at all.
No. Why? Yeah, because it's still it's a little compiled. Like why? Just out of curiosity, like why would you think that?
I was wondering, like having, for example, I don't know.
No, I mean, I didn't mean to call you out. I'm just because you look shocked. That's why. I was just making sure I'm not missing something. That's all. Yeah. Yep. Sorry.
Maybe to the question about the synchronization, there's a layer on the Rust library from Zephyr that only has new-built container form support. So it's minimal, but there are some primitive libraries which are similar to what you use in Rust normally. But the question to you is, what do you think about the future of this Rust Zephyr support now? Because it was developed by more than one person, maybe two contributors.
Yeah. I mean, it's pretty new. Like, I think the PRs, I think the issue started in like 2023, and then I haven't tracked like, the actual kind of, the history of the PR itself. I mean, there's no technical PR because it's still like not part of the main repository proper, so it's still kind of on its own. But I think like naturally, like it's just gonna. I again, if you look at the Linux kernel, right, there's more and more developers that are kind of migrating to Rust. So I think naturally the same thing is going to happen where we're just going to have more developers that are just naturally going to contribute more in Rust, right? And they're just going to build their own infrastructure in place if there isn't one, right? And the community is just going to is going to get behind it. I don't know. That's just my personal opinion. I think, yeah. I'll go there. Sorry. I think there's initial I think there's initial support for kind of abstracting. Again, it's that interface. So I know that I've seen like GPIO controllers and Flash controllers. I know there's an interface provided to the underlying device, like the device construct, right, for it. So I think that's a good starting point. And now we have to see, because again, it's not just a driver. It's like, well, let's say you want to write a sensor driver. Well, you have the sensor API, right, that you have to fit into, right, that subsystem. So then what's a sensible location in Rust to provide that API, right? Where do you draw that line? So I think the existing kind of implementations for like the GPIO controller and Flash controller may be good kind of sources of inspiration. But, it's just going to see like as people contribute to it, just the back and forth, right, of the project in general. Yep.
Question about testing. So you mentioned that you use the testing similarity. You certainly write good tests of the Rust code in Rust as well, and instantiate is part of that. Is that piece integrated into Zephyr system testing already?
No, I don't think so. Yeah, no, this is just like something I want to explore next, right? Because again, like just how I use Zephyr personally, like it fits nicely into, Rust just provides testing like out of the box too, right? So it's just like, it just makes sense that this would be the next thing that, maybe Zephyr, like the next easy thing that we could just throw into Zephyr as part of Rust, right? Just leverage that unit testing because, and then, personally, I think it would encourage more developers also to start writing kind of unit tests for Zephyr too. Yep. So.
Standard string formatting in Rust is pretty heavy, which is also used by the block rate. We also saw you need an increased stack size for that. Is that something that people are looking at?
Yes. Yeah, I think I saw like a few comments and a few to-dos that are like, it's there and there's like a print K and like, architecture specific kind of logging mechanism. And like, I think in the PRT.conf, like we saw like RTT logging is disabled, right? So I think there is an effort to kind of, like be more intravenous about logging rather than just use a log crate and start kind of re-implementing some of the features. So I think that's an effort, but it's just like, something quick. Yeah, I think that's all. I think I'm over. All right. Thank you, everybody.